Hi everyone, we are on to our second to last modality, which is our laser and light therapy. So you had a video up on Moodle to kind of review light and how light travels both as a wave and a particle and what a photon is and all those kind of things. So before we go into actually understanding how we use light for what we call photobiomodulation, or how we use light to affect the body, you need to kind of understand a little bit about light. And so when we're talking about our laser therapy and our light therapy, we're typically talking about the range of visible light and usually into infrared or ultraviolet. So ultraviolet is usually less than 380 nanometers as a wavelength. Our visible light is between 380 and 780, so with violet of the spectrum being on the lower end and our reds up near the higher end. And then our infrared, we usually look greater than 780. And so our light therapy is typically going to show up within this range. So what is light therapy? So it's also known as phototherapy, or low-level light therapy, or low-level laser therapy, cold lasers or cool lasers. There's lots of different kind of words for this, but for the most part, when we're talking about phototherapy, there's a set way of utilizing the light to affect the body. So, which is our goal. So the application of light by a variety of devices for some sort of therapeutic purpose. These are the different devices that have been used in light therapy. So lasers being the most common, and that's what we're going to focus on. We'll talk a little bit in a couple slides on LEDs and SLDs, but otherwise infrared lamps, ultraviolet lamps, fluorescent lamps. These are all more so used in like seasonal affective disorder or some skin conditions or some different things like that. So talking about a laser, laser actually stands for something. It's a mnemonic. So LASER stands for light amplification by stimulated emissions of radiation. So L for light, A for amplification, by, S for stimulated, E for emissions, of, R for radiation. So light amplification by stimulated emissions of radiation. The idea being that it transfers or transforms the electromagnetic energy of various frequencies, kind of again in or near the range of visible light. So either slightly ultraviolet within visible light or slightly infrared, depending on the wavelength that the particular laser is calibrated for. You get an extremely intense, small, and nearly non-divergent beam of monochromatic radiation. So it has all of the waves in phase. So this is really important. So lasers have very distinct characteristics compared to like a light bulb. Okay, so think of the difference between your little laser pointer, right, and a flashlight. Okay, we're going to talk about those differences. So lasers are monophasic, meaning that all of the light is in the same phase, okay, as far as being kind of in line. Monochromatic, okay, which means that there's a single frequency, or if we were talking about visible light, a single color. So the frequency of all of the light coming out is all the same. Okay, and we know in like visible light, that's not true. We're getting multiple wavelengths, right? So when light shines through a prism and we separate out those wavelengths, we're showing that we get all those different wavelengths. If you put a laser through a prism, you would just get the laser beam on the other side because there's no other wavelengths, no other frequencies for the prism to split the light in between. So it's all monochromatic. It's also coherent, which means they're all in phase with each other. And it's non-divergent, which means that it's all collimated. You have a single point. So again, comparing a laser pointer to a flashlight, where we would have that more divergent beam in the flashlight. So that's really important. Those four things is what distinguishes a laser: monophasic, monochromatic, coherent, and non-divergent. So also when we're kind of talking about lasers, there's terms you want to kind of understand. So a laser device is the machine or the device that produces, generates, emits the laser beam. The laser beam itself is the output of light. So again, that's monochromatic, coherent, non-divergent, monophasic. Laser light is the actual light of the beam, and laser energy is the energy of the beam. So how we get the light to be monophasic, monochromatic, coherent, and non-divergent is what makes it a laser. So inside the laser itself, we're going to have some sort of medium that we can stimulate. And that medium is going to be all the same particle, all the same molecule. And that's going to be really important because that's what's going to give us the very specific frequencies that's going to let us have those four aspects of a laser. So let's talk a little bit about light and laser production. And you'll also have a video up on Moodle for you to look at of how lasers produce their light. So remember from the video previously that light travels in particles and in waves. Okay? The wavelength is how it travels. The particle is how it is absorbed or emitted. A photon, when we talk about a photon, the amount of energy a given photon, so the given unit of light, has is a function of its wavelength, which is correlated to its frequency, because each photon has a unique wavelength and unique frequency. So the wavelength and the frequency are going to be related to each other. We kind of use them interchangeably. They're inverses of each other. So a longer wavelength will have a smaller frequency because light is always going to travel at the speed of light within vacuums. So when we talk about composing a laser, there's four areas that you would need to have. You need to have an amplifying chamber, which is the tube of the laser, if you will. Inside that amplifying chamber, there needs to be the lasing medium or the active medium. And again, that medium can be a gas, a liquid, it could be a crystal, just like our ultrasound. It could be a chemical, or it could be a semiconductor. And all of that is one chemical, one unique thing, because that's going to what's set us up for our photon to have that specific wavelength of energy. And then we have some sort of external source of power, which is most often electrical, battery operated, or from the wall. So it could also be chemical, it could also be optical. And then you have a pair of mirrors. So on one end you have a completely silvered mirror, just like a normal mirror. And on the other one you have something that is less than 99%. So of a mirror. So some light will escape out of this mirror. Okay? And those are set on opposite ends of the amplifying chamber. Okay? So as we apply energy to the lacing medium, the atoms inside the medium are going to absorb the energy. Okay? And when energy excites the atom, it causes the electrons on the outer layer of the atom. Okay? So a little review of atom science here. So it is going to stimulate those electrodes to jump up to, those electrons to jump up to a higher orbit. And then, as most things want to do, that's an unstable situation for that atom. So eventually it's going to want that electron or those electrons to drop back down to their resting orbit. Okay? And when they do, when they return to normal, they release that energy that they absorbed, because energy can neither be created nor destroyed. So they release it in the form of a photon. And so identical atoms with identical excitation are going to emit photons of identical wavelengths. So because all of the medium inside that laser is all the same atoms, they're all stimulated the same way, they all release the same type of photon with the same wavelength or frequency. So by using a specific lasing medium and controlling the process, the released photons are monochromatic and they're coherent. So they're all in phase with each other and they are all the same wavelength. A photon will strike the mirror at an angle, okay, and reflect back towards the other mirror. And they'll continue to bounce back and forth between those two mirrors where then they actually stimulate more of the atoms. And those atoms will then return to, the electrons will return to their resting state and produce more photons. And it keeps building inside. This is what we call the cascade effect. And these photons keep building inside. And as they keep bouncing back and forth, eventually some of them escape through that partially silvered mirror, and that's the beam coming out, okay? So that's how a laser forms. So the next video that you see, you'll be able to see that kind of displayed in a visualization, okay? The energy levels of the laser determine what they're used for. So high levels are typically used in like manufacturing, like soldering or welding. We're using what we call low-level lasers for their therapeutic effects. And those low-level lasers typically are less than 500 milliwatts. Okay. So before you go watch the video on the laser production, just a little bit more on the classifications of lasers. So the FDA Center for Radiological Health and Laser Classification System. So the FDA classifies lasers 1 through 4 with classes, 1 being the lowest risk. Okay, so it's the potential for the amount of power that the laser can produce. So somewhere between 1 and 4. Typically our treatments, okay, are somewhere around about 3A, 3B. Okay, 3B, 3A are usually typical ones. So 3A laser have an output up to 5 milliwatts. 3Bs are 5 milliwatts to 500 milliwatts. So those typically are kind of in our way. The biggest thing is that lasers can have effect on the eyes, okay, the laser radiation. And because sometimes it's not visible light, you don't have a blink response, so it doesn't protect your corneas, or your retinas, I should say, and it can burn out your retina. And so most of the laser systems have goggles you can wear, or you have to cover the laser device with a towel or a sheet or something like that, so that there's no risk of you potentially affecting the light into someone's eyes or something like that. We also have different types of lasers based on, and they're named for what that lacing medium is going to be. So these lasers have argon in their amplifying chamber. These ones have helium neon. And so you can see the abbreviations there. Different mediums, again, are going to produce specific wavelengths. And those wavelengths can then affect the treatments that we can potentially do, or the benefits that we could see with the laser therapy. So the medium determines the wavelength, which then affects or determines the physiological effects of the laser.